Mr. Chairman. Today I will talk to you about traditional technique used to protect metallic material against corrosion in many aggressive environments. The decarbonizing was discovered about 200 years ago. In the last years, scientists try to find new path, zinc-based path, in order to optimize some properties. One of these is to try to change the color of the surface. It is 200 years that we found it, that you found it. 5 or 6 years ago, we changed the color by using titanium in addition in the bath, and with a collaboration with Professor Natali, today we are able to change the color and control the color in a robust control during the process. So, today, this is the aim of our work, is to study the differences between the traditional hot decarbonizing coating to our innovative coating with presence of titanium, and it means to change the difference in terms of phases that this coating is made. The process is the same. We have the first phase is the cleaning of surface in order to eliminate the impurity. The impurities can be in two types. The first one is fatty impurities that we can clean by using tensioactive solutions. And the second one was the oxide or iron oxide impurities that we can eliminate by using acid solutions. Sometimes we use chloride acid in percent, 50% of concentration of this acid in solution. Other one uses sulfuric acid, 20%, but at high temperature, about 15 Celsius degrees. Then we flux the surface by using zinc chloride and ammonium chloride salt in order to improve the formation of coating. Drying the surface because it is dangerous to dipping wet metals in the bath at high temperature. We can have an explosion. And finally, a dipping in the bath containing 0.5% of titanium in our case. In this case, we have interdiffusion of ions of zinc and iron on the surface. This is a section of coating. We have the different region characterized by different chemical composition. In this zone, we have a much more presence of iron. And in the outer zone, this is the surface, we have a presence of mainly zinc. In the intermediate zones, we have a presence of different intermediate phase. According to this diagram, we have presence of a brittle phase up to 18% of zinc. Sometimes name it as capital gamma letter. Then we have a delta phase in this concentration, corresponding to this thin coating. Zeta phase, characterized by columnar morphology. It's a very funny phase because it's very simple to discover. And then we have in the outer zone the presence of eta phase. The chemical composition of eta phase is quite similar to the composition of but is due to wettability of metal on the surface. The presence of this phase is due not so much for interdiffusion phenomenon. This is a traditional optical galvanizing coating. In our case, we use an addition of titanium, and here you can see the presence of the different surface with different color. This is not a painting, it's the real color of coating. You have a golden yellow, purple, blue, light yellow, pink, green, and so on. There are the differences between this coating with respect to the traditional coating. So, in order to find the microstructural differences, we make all these investigation. Simple observation in sand, XRD analysis, microbeakers analysis in order to find the difference mechanical behavior, and then test made yourself. It consists in a sort of shock of a simple ball that goes down on the surface starting at, I remember, 1 meter to respect the surface. The mass is about 1 kilo of ball. So this is the first results. We can see the presence of the additional phase A, indicated with this letter. This is a capital lambda phase. It's very thin phase. Sometimes the thickness is about 3 atoms, not observable by using the traditional microscopy. Then we have the presence of delta phase, indicated in letter B, and the outer region is formed by means of a matrix C, is a matrix, an eclectic phase, in the presence of compact phase, indicated by means of letter D, is the main differences, the main difference between the traditional to our innovative coating. We have named this phase as tau phase. XRD diagram, diffractogram, present different peaks. You can see the peaks indicated by a box dot, black dot. And analysis of this spectra shows the presence of a phase much more rich in titanium and iron. Other analysis of morphological position shows the position of this phase along the longitudinal direction parallel to the surface, we show the formation of this phase from the delta phase, and then we have a moving of this surface, this phase toward the external phase. Okay. The chemical composition is this: titanium 3%, iron very high, 7%, and 19% of zinc. The chemical formula is this: titanium 2, iron 22, zinc. It's a compound. So, from the point of view of micro hardness, we can see the presence of this shape is very, very short if compared to indentation carried out on other face. This is the matrix, this is a delta phase. The micro-hardness of delta phase is comparable to micro-hardness of iron.
Okay.
Thank you. We have values of hardness is 4 times much higher. And finally, this is the damage due to shock on the surface. You can see the presence of radial crack starting to brittle phase upper to outer phase. Outer phase ductile is a simple thing. In this case, we have a presence of tau phase, and tau phase can assume a sort of way to propagation of cracks from the inner zone to the outer zone. In this case, we have a loss of barrier protection of the metal. So, conclusion, the new coating is colored, but it is not very good in many applications where the loads are instantaneous. It's good for application where we have a static or very static, no so quickly change of loads. Thank you for attention.